Reflection and curved mirrors. In this lesson, we'll be talking about concave and convex mirrors, including the terminology, focal point, and drawing ray diagrams for each one. Lastly, we're going to talk about how to find images in both concave and convex mirrors. Terminology. So when we're talking about our different types of mirrors, the center of curvature is going to be the middle of what would be the circle. So you can see in the bottom left-hand corner here, if we were to extend this circle outwards, we would see that they would connect. I'm not quite enough room on the bottom here, but you can see that they connect. And then the middle of what would be that circle of the two different lenses, and what would be the middle of the circle of these two different mirrors, would be the center of the sphere, which we have located right here. Focus, otherwise known as the focal point, or F, is where the reflected rays all intersect. The principal axis, the PA, is the line drawn through the center of the mirror and meeting the mirror at 90 degrees. So that's going to be this red line right there. And the vertex is the exact point where the principal axis meets the mirror, which is located right there. Recall. Light rays always have an angle of reflection equal to the angle of incidence. This angle is between the ray and the normal, which is 90 degrees to the mirror surface at the point where the rays hit the mirror. So you got to keep that in mind as we go through this lesson. Concave mirrors are also known as converging mirrors, as the light converges at the focal point in front of the mirror and creates a real image. So there's going to be a concave mirror right there, and you can see the focal point is in front of the mirror. Convex mirrors are also known as diverging mirrors, as the focus is found behind the mirror and is found by tracing the reflected rays in a straight line. So you can see the focus is here, and they're going to be virtual rays because we see the dotted, and how we find them is by extending. So there we go, we get our incident ray, this is our reflected ray, and what we're going to do is we're going to extend the reflected ray back. And as we extend all the reflected rays back, they meet up at the focus. So you can see the focus is where the rays meet. For a concave mirror, it's where real light rays meet, and for a convex mirror, it's where the virtual rays meet. Focal point, concave mirror. We can use rays parallel to the principal axis to find the focal length of a concave mirror. Again, the focal length is where all the rays that reflect off the mirror are going to meet. All parallel lines will reflect into the focal point. So you can see we have a parallel line here, a parallel line there, there, and there. And whenever they hit the mirror, as long as they're parallel to the principal axis, they're going to bounce back into the exact same spot. And right there, they're all going to hit at the exact same spot, which is the focus. Now here are our concave mirror rules. Number one, a light ray parallel to the principal axis is reflected through the focus. This is what we were just talking about. So anytime we draw a light ray that hits the mirror that is parallel to the principal axis, it's going to reflect off the mirror and go through the focal point. Number two, a light ray through the center of curvature is reflected back on itself. So you can see this black line here. If we extend it from the center of curvature to the mirror, it's going to hit that mirror and it's going to come right back along the exact same line. Number three, a ray through the focal point will reflect parallel to the principal axis. So this is the reverse of rule number one. So if we send a ray through the focal point and it hits the mirror, it's going to come back parallel to the principal axis. And number four, a ray aimed at the vertex will follow the law of reflection. Just like it will no matter where you hit on the mirror, it's just going to be a little bit more obvious when it hits the vertex. Remember, the vertex is where the principal axis hits the mirror. Any incident ray is going to have an angle, so that's going to be our angle of incidence, and that angle of incidence is going to equal the angle of reflection, as we've talked about before. Again, that's no different than any other point in the mirror. It's just something that we can observe, and we can use that rule to draw our ray diagrams later on. Now, to locate your image using a concave mirror, you need at least two rays coming from the object. Everything's going to come from the object, keeping in mind that there's a light source somewhere. So let's just say it's the sun here. And it's reflecting light off the object. So those light rays are going to hit the object and go in every single direction. We just need to pick two of them. Now, where the rays meet after reflecting off the mirror is where the image is located. If the rays do not intersect, you need to trace them back to the point where they do intersect. You can use any of the four rules, but these are the two easiest rays to use most of the time. Number one, a parallel ray is reflected off the mirror and then through the focal point. So if we take a ray from the top of the object, we hit the mirror and then we go through the focal point, that gives us one of our rays. Number two, a ray is sent through the focal point and reflected parallel to the principal axis. So we start at the same point at the top of the object, we go through the focal point, hit the mirror, we reflect off the mirror, and we get our second ray. Now where those two rays meet, that's going to be the same point on the image that we started out from the object. So since in the object we start at the top of the arrow, that is the top of the arrow on the object. We could do that all the way down the object, and eventually what we would do is we would make a shape that looks exactly the same as the object, but as the image. So for each of these, I want you to describe what the image looks like. Remember, the image is the thing created using the reflected rays, using our SALT, our size, attitude, location, and type. So let's start with this one. So pause the video and describe the image using SALT. Okay, so this one, you can see that it's smaller. It's inverted, it's between C and F, and it's real. So when we're describing the location especially, we're going to pick some points on the principal axis that we can see. In this case, we know that their C value is right here, and we know the F is right there. Okay, pause the video and try this one. This image, again, is smaller, it's inverted, it's between C and F, and it's real. How about when the object is at C? When the object's at C, it's going to be the same size, it's inverted, it's at C, and it's real. How do we know it's real? It's real because there are real light rays making up the image. They're actual rays that are bouncing off the mirror and creating that image. Object between C and F. We get a larger, inverted, beyond C, real image. At F. This one's a little bit trickier, so have a look at the rays that are drawn and see what's going to happen. In this case, no real image is produced when the object is located at the focal point, as the reflected rays are parallel and will therefore never intersect. So this guy right there and this guy right there are parallel to each other. Therefore, they're never going to intersect. Therefore, we can never make an actual image. So if you have an object at the focal point of a mirror, you're never going to be able to see the reflected image in that mirror. Object is between F and the mirror. When it's between F and the mirror, you get a different kind of image. In this case, it's larger, it's upright, it's behind the mirror, and it's virtual. Why is it virtual? Because these rays aren't real. Keep in mind the mirror is opaque. Light rays can't actually pass through the mirror. So when they hit the mirror, they reflect off. Now what our brain does is that we extrapolate those lines and we say, okay, we know those light rays travel in a straight line. So this reflected ray must have come from back here. This reflected ray must have come from back here. So what are the uses of concave mirrors? Well, searchlights, car headlights, and flashlights all use concave mirrors to create parallel or almost parallel beams of light. So why do you think that is? We'll come back to that in a second. Telescopes and satellite dishes also use concave mirrors to focus electromagnetic waves at the focal point. Again, why do you think that is? Okay, so let's go back to our first one. So when we're talking about things like searchlights, car headlights, and flashlights, what we want is we want a narrow beam of light, as narrow as possible. It's going to diverge a little bit, but we want that beam as narrow as possible. Now, if we were just to set up a light bulb, remember, a light bulb is going to shine light in all different directions like the sun, and that's not going to give us a very concentrated beam. So what we want to do is we want to have some kind of concave mirror behind our light bulb. So there's our light bulb. And we're going to put that light bulb right at the focal point. If we put that light bulb at the focal point, then all the rays, remember our rule number one, all the rays that come from the focal point are going to hit the mirror and come out parallel to each other. So our light bulb is going to give out rays in every single direction, but since they're all coming from the focal point, they're all going to come out in the same orientation, which is going to give us a much stronger beam of light. Now for satellite dishes and telescopes, it's kind of the opposite. Again, we have a concave mirror. In this case, we're going to have at our focal point the sensor, so the thing that's going to take in the information. Now, we're talking about a satellite. You got to keep in mind that the things that it's pointing at are really, really, really far away. They're so far away that, in essence, the light rays that come to the telescope or the satellite dish, they're all parallel to each other. Now, they're not quite parallel to each other, but they're pretty close. And what happens is any ray that's parallel to the principal axis is going to hit the concave mirror and reflect directly into, you guessed it, the focus. Since our rays are going to reflect directly into the focus, we know we're going to get a strong signal of whatever it is we're looking at. And that's what we want. We want all the rays, so say they're television signals, coming in and hitting the sensor so that we get the strongest possible signal. It doesn't matter if they're coming in from right at the edge of the dish or right near the focal point. They're all going to reflect into the exact same spot, which is going to allow us to really get a good signal of what it's looking at, because the thing taking in the information is located at the focal point. Other uses of concave mirrors. Remember back to this example here. When our object is between the focal point and the mirror, we get a larger image. Now, if you want to take a look at yourself in the mirror, or you want to see whatever it is you're looking at more up close, you want a larger image. And that's what we can do. All we need to create is a mirror with a very far focal point. So if you take a look at this example here, this person is using this mirror. Since the mirror is not curved very much, maybe the focal point is out here. If the focal point is out here, then she is going to be between the mirror and the focal point. And what she's going to see is a larger image of herself. So we can use it to magnify what we're trying to look at. Now, let's take a look at convex mirrors. Convex mirrors are diverging mirrors, and for convex mirrors, the focal point is on the other side of the mirror. In this case, since our mirror is bulging out to the left, our focal point is to the right. It's always going to be on the other side of the mirror. It can be found by drawing lines parallel to the principal axis, and then we're going to extend the reflected rays past the mirror. So that's what we see in number 2. So number 1 is the incident rays coming in, hitting the mirror, and number 2 are the extended reflected rays going backwards. And you can see they all meet at the same point, the focal point. Center of sphere is the same thing. It's again to the right, just like the focal point is to the right, and it can be found again by drawing a line perpendicular to the mirror at any point. We're going to extend the rays past the mirror, and where they intercept the principal axis is the C. Now, the difference between concave mirrors and convex mirrors is that in a convex mirror, F, now called the virtual focus, and C are behind the mirror, and light rays seem to come from an apparent source behind the mirror. Different from a concave mirror, where we're creating a real image from real light rays. Okay, so just like for concave mirrors, we have some rules for convex mirrors. Number one, a ray parallel to the principal axis is reflected as if it had come through the focal point. So you can see here we have a ray that goes into the mirror. It's going to reflect off the mirror, and it's going to reflect off as if it came from the focal point. So we can put our ruler at the focal point, and then we can draw a straight line, dotted line for the virtual rays until it hits the mirror, and then a solid line. And you can see that with all of our different rays. You can see this ray coming in here is going to hit the mirror, and it's going to be reflected as if that ray came from the focal point itself. Number two, a ray aimed at the center of curvature is reflected back upon itself. So the ray goes in, and then the ray comes back out, and then we can extend that reflected ray back to where the center of curvature would be. Number three, a ray aimed at the focus is reflected parallel to the principal axis. So if we're going to aim it at the focal point, and if it were to hit that focal point, instead it's going to hit the mirror and bounce off parallel to the principal axis. So when we're drawing ray diagrams using convex mirrors, we again need two basic rays. The first ray we're going to use is a parallel ray that extends from the top of the object to the mirror, so it's going to be parallel to the principal axis, so that's this guy right here. It's going to hit the mirror and reflect back as if it came from the focal point. That's going to be our first ray. Our second ray is going to be a ray directed towards the focal point, so that's this here, again from the top of the object. It's going to be aimed as if it were going to go right through the focal point. It's going to hit the mirror and come back parallel to the principal axis. Now if we extend both those rays out, they're going to intersect, and where they intersect is going to be at the top of that image, just like we started at the top of the object here. Images in a convex mirror. The rays reflected off a convex mirror always diverge. Reflected rays from an object never cross in front of the mirror to form a real image. Instead, they always create a smaller, virtual, upright image. So unlike our concave mirrors where we can get a different kind of image depending on where the object is located, in a convex mirror it's always going to be a smaller, upright, virtual image. Now what are some uses of convex mirrors? Well, you've seen a lot of these. If you go to like some kind of convenience store, you'll see these mirrors that look like this located in the top corner so the owner can see around his or her store. And you can see these mirrors in cars. Now, the funny thing about the car side view mirrors is that they always say objects in mirror are closer than they appear. So what I want you to do is I want you to pause the video and think about why that is. Why our images in a car's side view mirror are always closer than they appear. Now, one phenomenon about the human brain that we think of large objects as close and small objects as far away. As we just discussed, any image created in a convex mirror will be smaller. So since our image is smaller than the actual object, then the images that appear in the car's side view mirror are going to be smaller than they actually are. If they're smaller than they are, then our brain thinks that they're further away because we know approximately how big cars are. And if we see a small car in a mirror, we think that that small car is a regular sized car, but farther away. Since it's not farther away, any object in a side view mirror will appear smaller, and therefore our brain will think it's farther away. So that's why you got to keep in mind that it's closer than it appears. And that concludes our lesson on reflection in curved mirrors.